You know, the phone or computer you're watching this on is an incredible piece of technology. But there are problems out there so massive that even our best supercomputers would need thousands of years to solve them. I'm talking about designing life-saving drugs molecule by molecule or inventing revolutionary new materials from scratch. These are the so-called impossible problems. But what if a totally new kind of computing could make them possible? Well, that is the promise of quantum computing, one of the most transformative technologies of our time.
Here's a pretty cool way to think about it. A normal computer bit, that's like a coin that's already landed. It's either heads or it's tails. Done. A quantum computer, though, works with that coin while it's still spinning. It harnesses that moment of pure possibility, where it's both heads and tails at the very same time. Now, I know it sounds strange, kind of counterintuitive, but that idea is the absolute key to unlocking a whole new dimension of computing power.
So, to really understand that power, we have to move beyond the simple on or off, the zeros and ones that have defined all of computing for the last century. We need to step into the quantum realm.
On one hand, you have the classical bit. It's reliable, it's simple, but it is fundamentally limited. It can only ever be a 0 or a 1. That's it. On the other hand, you have the quantum bit, or qubit, and this is where everything changes. A qubit can be a 0, it can be a 1, or it can be a combination of both of them at the exact same time.
This wild ability to exist in multiple states at once has a name. It's a quantum phenomenon called superposition. And because a single qubit can hold so much more information than a classical bit, it means a quantum computer can explore a vast number of possibilities all at once. It's like parallel processing on a scale that classical computers can only dream of. But you know what? Superposition is just one part of the equation. There's another, even stranger quantum phenomenon that links these qubits together, and that is what unlocks an exponential leap in processing power.
And that phenomenon is called entanglement. You can think of it as a mysterious connection between two qubits. Once they're entangled, they act as a single system. And here's the crazy part. If you measure one, you instantly know the state of the other, even if they're on opposite sides of the universe. It's this deep, spooky connection that lets quantum computers solve these incredibly complex problems.
So how powerful is this combination of superposition and entanglement? Well, get this. A quantum computer with just 300 entangled qubits can represent more states at the same time than there are atoms in the entire observable universe. Just let that sink in for a minute. That's the almost unimaginable computational space we're talking about here.
Okay, so we have this mind-bending power, but what can we actually do with it? This isn't just some theoretical exercise. It's about solving some of the world's most difficult and important problems.
For example, in healthcare, quantum computers could simulate molecules with perfect accuracy, which would totally revolutionize drug discovery and pave the way for personalized medicine. Or in materials science, we could design new superconductors from the ground up, or create way more efficient batteries, tackling huge challenges in energy and climate. And the impact stretches into finance and logistics too. Quantum algorithms could optimize incredibly complex systems, like managing global supply chains to reduce waste, or analyzing financial markets to better manage risk. It could even supercharge AI for things like real-time fraud detection, finding patterns that are just invisible to us right now.
This power to build and to optimize is just incredible, but it comes with a profound challenge. You see, a tool that's powerful enough to design new medicines is also powerful enough to break the very codes that protect our entire digital world.
And that right there brings us to the great paradox of quantum computing. The very same properties that make it so powerful also pose an existential threat to our modern cryptography, the stuff that protects everything from our bank accounts to our national security.
This threat actually has a name, Shor's algorithm. And this isn't some far-off theory. It is a concrete set of instructions for a quantum computer. See, most of our modern encryption is built on a simple mathematical trick. It's easy to multiply two large prime numbers together, but it's incredibly difficult to take that result and find the original primes. For classical computers, it's practically impossible, but for a quantum computer running Shor's algorithm, it's trivial.
This has sparked an urgent global race. Researchers and governments all over the world are working to develop new encryption methods that are secure against both classical and quantum computers. It's a field called post-quantum cryptography, or PQC. And it's a critical effort to upgrade our digital infrastructure before it's too late.
So, that brings us to the big question. Where are we right now? How close are we to these powerful, world-changing machines? Let's take a look at the current state of the race.
We are currently in what's called the NISQ era. That stands for Noisy Intermediate Scale Quantum. What that means is we have processors with hundreds, even over 1,000 qubits, which is incredible. But they're also noisy. Imagine trying to have a perfect whispered conversation in the middle of a rock concert. Even tiny vibrations or temperature changes can disrupt the delicate quantum states, creating errors that limit what they can do today.
The progress in just raw power has been staggering. The number of physical qubits has grown exponentially over the last decade. Companies like IBM, Google, and D-Wave are in a fierce race to scale up their hardware, and that steep upward curve you see, it's just undeniable. But here's the catch. It's not just a numbers game. Quality is just as important as quantity. The real goal isn't just more qubits, but better qubits, ones with lower error rates. The ultimate prize is a fault-tolerant quantum computer, one that can automatically correct for all that noise, allowing it to run powerful algorithms flawlessly.
And this race isn't being run by just a handful of players. It's a massive global ecosystem. You've got university research labs, nimble startups, and the biggest tech corporations on the planet all pouring immense amounts of investment and brainpower into turning this revolutionary science into a world-changing technology.
So, this isn't science fiction anymore. The fundamental science is proven, the hardware is scaling up exponentially, and the very first practical applications are starting to emerge. The challenges are enormous for sure, but the potential rewards are even greater. The quantum revolution is no longer a question of if, but when. The real question is, are we ready for it?